All right, so I'm going to start with 10.1 because I like it. All right. So 10.1 is an introduction to real numbers. So this little diagram here is talking about some of the different types of numbers. So notice that it's set up this way for a reason. So each one of those sets is like nested inside the other. Okay, so you have the smallest one, which is the natural numbers. And so that's also known as the counting numbers. So it starts with 1, and then it just counts all the way up from there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, et cetera, forever and ever and ever. So any positive whole numbers are natural numbers. And then outside of that, we have the set called the whole numbers. And there's literally only one number different between the natural numbers and the whole numbers, and that number is 0. So the whole numbers includes 0, the natural numbers does not. All right, so let's see, then outside of that, we have the integers, and we talked a little bit about integers before. So the integers includes all of the whole numbers, plus it includes all of the negative whole numbers as well. And then outside of that, we have the rational numbers. So a rational number is anything that could be written in the form of an integer over another integer. Okay, so it includes all the integers, plus it includes basically fractions. It also includes most decimals as well, because, for example, if you have 0.3, well, you could write that as 3/10, 3 over 10, which would be an integer over another integer. So most decimals are also included in rational numbers. And then outside of that, we have the set called the real numbers, and that includes things like the square root of 2, the square root of 3, the square root of 5. It includes things like pi. So pretty much any square root that doesn't have a nice answer is going to be not classified as a rational number, so it would have to be just in the real number set. So numbers, we do have a special word for those numbers, like the square root of 2, which is irrational. So numbers like the square root of 2, so any number that is a real number, but it's not rational, it is described as irrational. Okay. So, all right, so I already said that a rational number is any number that can be written in the form of a over b, where a over b are integers and b is not 0 because you can't divide by 0. Okay, so question number 1 here says, which of the following is not an integer? What do you think? That's correct. D is not an integer because it is not a whole number, it's a decimal. Okay, now C is an integer because the square root of 100 is equal to 10. So that is an integer. All right, number 2, which of the following is a natural number? Nope, negatives are not natural numbers. Which of the following is a natural number? Right. So again, since the square root of 100 is 10, and 10 is a natural number. So all of the rest of those are not natural numbers. So 0 is not a natural number, a negative can't be a natural number, and a decimal can't be a natural number. And number 3, which of the following is not a rational number? What do you think? Anybody have a guess? Pi is not a rational number. Yeah. So, yep, it is a real number, but it is not a rational number. So it is also could be described as an irrational number. So some of those middle school math teachers, they have those borders that go all the way around their whole classroom with digits of pi, right? And if their classroom had the size of infinity, it would still keep on going. So yeah, so when you look at, like, when you type an irrational number into a calculator and you look at the decimal approximation, you're going to see that it has a bunch of random numbers after the decimal point, and it goes on forever. It has no ending point, and it has no repeating pattern. Okay, so by saying that on this question number 3, I'm also saying that all of these other options are classified as rational numbers. Okay, so all like integers are rational numbers, and also most decimals are rational numbers. So any decimal that does not go on forever is also a rational number. Okay, so like, for example, 4.5 is what they call a terminating decimal, meaning it actually stops at some point. It doesn't go on forever. So any terminating decimal is a rational number. Okay. All right. Let's see. Yeah, I'm going to go ahead and hand you this test review because there's a problem on here that I want you to look at. And it's like on the second to last page. This one right here. It looks like that a big set thingy. Oh, battery. Computer battery is low. Okay. Okay, so let me do this real quick. Let me just throw something out here. Okay, so let's say, for example, I'm going to make something up. I'll just do like that. Okay, so let's say we had, this is, the big circle represents any real things. And let's say this one represents food and this one represents candy. Okay, so let's say I wanted to figure out where am I going to write the word pizza. Okay, well, pizza would be in this section here. Okay, pizza is a food. It's not a candy, but pizza is also a real thing, right? So the whole food circle is completely inside the circle of real things. So I don't need to write pizza over here again because it's already in there. Okay, so when I fill out a diagram like this, I actually only need to write each number or each, in this case, each thing one time. Okay, so like, let's see, a chair, if I was trying to classify the word chair, I would put it in there with real things, but not with food or candy. Okay, and let's say if I had the word Snickers, I could put it in here in the candy blob. So Snickers is a candy, it's also a food, and it's also a real thing. But again, it's once I write it in the small circle, it's already in all the bigger circles as well. So I don't need to keep writing it in every circle. But it is true that it is a food and it is a real thing. Does that make sense? Okay, so when you look on your test review, like I said, I think it's like the second to last page. Yeah. And so I have a diagram like that on the test review for the different sets of numbers. So when you fill out that diagram, you're only going to write each number one time. Just write it in the smallest circle that it fits into. And that means that, yes, it also fits into all the larger circles as well. Okay, so for example, if I had, the number 5, so I'm just going to use some other examples other than the ones that are, other than the ones that are on there. I need to. Okay, so for example, if I wanted to do, make that go away. Make that go away. Oh, okay. All right, so if I wanted to put the number 5, I would just write it in there. If I wanted to do, like, let's say, negative 4.2, I could put it there. So I'm just making up some numbers, but the only number that would ever be written in this area is 0, because that's the only number that is a whole number that's not a natural number. Yes. It wouldn't be 2.5. No, it would be something, yeah, it wouldn't. Because, let's see, the square root of 5 is that. Yeah. So pretty much, you'll pretty much know, like, so, you have like 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. So if it's not something, because the square root of 5 is asking what number multiplies times itself to equal 5. So you're probably thinking of like dividing it by 2. 5 divided by 2 is 2.5, but that's not the same thing as saying the square root. Yeah, so like for example, the square root of 4, well, that's a bad example. Square root of 9 is 3 because 3 times 3 is 9. And the square root of 16 is 4 because 4 times 4 is 16. Yeah, so if you had something like, if you had, for example, the square root of, let's say, 25, then actually I would put that in here because the square root of 25 is 5. So those are the kind of things you'll see. I mean, it'll either be a nice perfect square like the square root of 25, or it'll be, you know, something else that is like the square root of 10 or something like that. Yeah, and if it was the square root of 10, you'd put it over here. Alrighty, good question. All right, any other questions about that? Okay. All right, I'm going to go ahead and go back to the notes. Okay. So this is just a little review of inequalities, making sure that you understand the inequality symbols and how to read them. So x, for example, x is less than 3, y is greater than 2. If it has the underlining underneath it, that means or equal to, so that would be a is less than or equal to b, 5 is greater than or equal to n. So number 4 says, write a different inequality with the same meaning as 9 is greater than p. So 9 is greater than p is the same thing as just flip it around and say p is less than 9. And number 5 says, write an inequality meaning g is less than or equal to -4. Okay, so that would look like that. Number 6, true or false. All right, first of all, you might want to be able to read what it's saying. So on number 6, it's saying -7 is less than 0. So is that true or false? That's true. Number 7 says 5 is greater than or equal to -2. So is that true or false? Okay, someone said false. Someone always says false. But it's actually true. So the statement says 5 is greater than or equal to -2. So it's only one of those can be true. They can't be both true at the same time. It's either greater than or it's equal to. So it's never going to be greater than and equal to, right? It's just going to be one or the other. So 5 is greater than -2, so therefore that statement is true. Okay, does that make sense? So you could also say, for example, you could say 5 is greater than or equal to 5, and that would also be true because they're equal. So when we say greater than or equal to, it just means only one of those statements is true. Obviously, it's never going to be both. Can't be both greater than and equal to, but it can be one or the other. So it just has to be one or the other for that statement to be true. All right. And number 8, so I need to simplify both sides of that. That says 8 minus 3 is not equal to 2 times 3 minus 2. So 8 minus 3 is 5. And then 3 minus 2 would be 1. So that would be 2 times 1. So that says 5 is not equal to 2. So that's true. And then number 9, -2 minus 3 would be -5, less than or equal to. And then -10 plus 5 is -5. So it says -5 is less than or equal to -5. So is that true or false? That's true, because they're equal. Okay. Any questions about that? Okay. And then I'll go ahead and do chapter 9. I did 10 first, like I said, just because I like it more. I just wanted to eat my dessert first. You guys will probably like this one more, though. I don't know. You just hate all of it equally. I don't know. All right. So this one is good. This chapter is good though, because it's all about like charts and graphs, like, but not graphs like graphs of, you know, y equals mx plus b, not really those kind of graphs, but like pictographs and bar graphs and, you know, circle charts or unit like pie charts or whatever. So it's those kind of graphs. All right, so, and I'm sorry that some of the images are kind of hard to read, especially with this projector. But this first couple questions is about this pictograph. And so what it is a bunch of okay, it's like almost impossible to see in here, but those are like little tiny pictures of like stalks of wheat. That's what they are. All right. So question number 1 says, which of the states shown plant the least amount of wheat acreage? So that's going to be Colorado and Washington, because they only have 2 of these little guys each. So the answer to that is Colorado and Washington. And then question number 2 says, approximate the number of acres of wheat planted in Kansas. Okay, so Kansas, we have 1, 2, 3, 4, 5, 6, 7, 8. And I don't know if you can tell or not, but this right here is supposedly like 1/2 of the picture on the end here. So it's going to be 8.5 million acres. Look at the little key down here. It says each one of those little pictures represents 1 million acres. All right, so 1, 2, 3, 4, 5, 6, 7, 8.5. So 8.5 million acres. And then question number 3 says, which state plants about 4 million acres of wheat? Okay, so 4 looks like, so Texas and Oklahoma look very close, but of course Texas always has to be a little bit better than Oklahoma. So again, if you can't tell, this one on the end of Oklahoma looks like half, whereas the one here on Texas looks like a whole. So the answer to this question is Texas. All right. All right, and then the next thing we have is another pictograph that represents wildfires in the United States in a given year. And the key down here tells us that each one of those little pictures of a fire represents 12,000 fires. All right, so question number 4 says, approximately how many wildfires were there in 2006? Okay, so 1, 2, 3, 4, 5, 6, 7, 8. and multiply that by the 12,000. So 8 times 12 is 96, so this is 96,000. Number 5 says, in what years were the numbers of wildfires greater than 72,000? Okay, so I'm going to do 72,000 divided by 12,000. So 72 divided by 12 would be 6. Yeah, 6. And so that would be 6. So I'm looking for more than 6 little pictures of fire. Okay, so 1, 2, 3, 4, 5, 6. So there's 6. So I want to look for the ones that go past that line. So in what years? So there's a tiny little piece here in 2002. And then 2006, 7, and 8 also. Number 6 says, how many more wildfires were there in 2006 than in 2005? Okay, so we have, so in 2006, looks like there's 8 of those little guys. And in 2005, looks like, let's see, what is that? 1, 2, 3, 4, 5.5. So I'll subtract 8 minus 5.5, and then I'll multiply that by 12,000. That's one way we could do it. So 8 minus 5.5 would be 2.5. So 2.5 times 12,000. And let's multiply that. So the way I would just kind of think I would do this in my head by saying 2 times 12,000 would be 24,000. And a half times 12,000 would, half of 12,000 is 6,000. So add those together, that's 30,000. Or you could just multiply it out with long multiplication like a normal person, I guess. All right, and then it says, what was the percent of increase in wildfires from 2005 to 2006? So in that case, you have to take the amount of the increase, which was 30,000, and you have to divide it by the earlier amount, which is whatever the amount is from 2005. So I probably should have calculated that earlier, but I didn't know well. So it was 5.5 times 12,000. Okay. So I pretty much know I can just cancel out 3 of those zeros. I don't know if that's a good idea or not. Let's see. Yeah, I might as well do that. So then 5.5 times 12 would be, let's see, 5 times 12 is 60, and then half of 12 is 6, so 66. So it'd be 30 over 66. So I could reduce that. They're both divisible by 6. 6 goes into 30 5 times. 6 goes into 66 11 times. So 5 over 11. but I'm looking for a percent. So I basically need to divide that 11 into 5. And I don't have to squeeze it in somewhere. So if I would go into 11, oh wait, that's backwards. I need to do 11 into 5, sorry. Okay. So 11 would go into 54 times, that'd be 44, 56, 25. And this is gonna repeat. So let's say if we just round it to the nearest hundredth, it would be approximately 0.45, which is 45%. Okay, so next we're looking at like a bar graph representing the number of hurricanes making landfall in the US by month. Okay. All right. Let's see. In which month did the fewest hurricanes make landfall? So just look for the shortest bar. So that would be June. Okay, easy peasy. So that's the only question for that graph. And then the next graph is a bar graph showing the population for some of the world's largest cities. And question number 8 says, name the 2 cities that have approximately the same population. So it's a little bit hard to tell exactly. If you're doing this on the computer or on a test, it would be, we would make sure that it's a little bit easier to determine, but we're just going to get as close as we can for this purposes. So there's a couple that look pretty close. LA and Shanghai look really close. I'd say that's probably the closest, although Delhi and New York look pretty close as well. But I think LA and Shanghai look the closest to me. Yeah, okay. How much larger is Mexico City than Shanghai? So Mexico City, can't draw a straight line, but it looks like it's about, let's see, that's 20, that would be 22, so that would be 23, approximately 23 million for Mexico City. And then Shanghai, it looks like 18. So 23 minus 18 would be 5, and that's in millions. All right, so the next graph is showing the number of adults who drive a certain number of miles per day. So probably based on like a survey is what it seems like. So how many adults drive between 200 and 249 miles per day? So it looks like, I would say 9. And then number 11 says, how many adults drive between 150 and 249 miles per day? So for that, we are looking from 150 to 249. So we would have to take these two and add them together, which they both look like 9s. So 9 plus 9 equals 18. And then number 12 says the least number of householders would be in what age range? So just look at the bar graph for the shortest bar, which is under 25. All right, and then here we have a pie chart, or they might call a circle graph, which looks like it's melting off the page, but let's see. And then of course some of my text has disappeared, so that's nice. Let's see here. Besides other arrangements, where it's supposed to say where do the least number of students live? Okay, so other arrangements is the little green thing. So the smallest one besides that would be own off-campus housing. And then number 14, find the ratio of students living in off-campus rentals to total, supposed to say, students. So to answer that, we would first need to calculate the total number of students by adding all of those together. So we have basically we're going to do 180 plus 320 plus 14 plus 62 plus 124. Add all those up. And that'll give us the total number of students in whatever this survey or college is. Okay, so that would be 500. And that would be 76. Okay, so 576 plus 124. So that would be 700 total students. All right, so that's the total. So find the ratio of students living in off-campus rentals. So off-campus rentals is 124. So it'd be 124 over the total students, which is 700. And then we would need to try to reduce that. So I think we could reduce by 4s for one thing. Because let's see, 4 would go into 124, and that would be 31 times. And 4 would go into 700. Let's see. Is it 175? Yeah. 31 over 175. Okay, here's another pie chart for, okay, so this one is showing the percent of the land on Earth that is taken up by each continent. So which continent is the smallest? That would be Australia. It's only 5% of the land on Earth. And then number 16, what percent of the land on Earth is accounted for by North and South America? So we have to add the North and South America. So that would be 16 plus 12. So that would be 28%. Okay, and another pie chart showing the percentage of different types of books in a library. Says what percent of books are nonfiction or reference. So we would add the nonfiction plus the reference. So that would be 25% plus 17% equals 42%. There's another missing word here. If this library has 125,600 books, how many books are, I think it was supposed to say reference, but it doesn't really matter. Okay. It's not supposed to. Okay, so reference books are 17% of the books. So if there was 125,600, so we'd have to multiply that by 17%. So we're doing this. And we need 2 of those digits to be after the decimal point. So I got 22,352. All right, and that's the end. Okay, so make sure y'all are doing your homework, and Tuesday, people, I'll see you for the test on Tuesday, so there won't be any Zoom for next week because we'll just be having the test. Tuesday, people testing on Tuesday, Thursday, people testing on Thursday. Must be present in the classroom, just like last time. And let me know if you have any questions. Make sure you do the review. Make sure you check the answers on Canvas. Mm-hmm. Mm-hmm. 12. If you go to that tutor, if you click on the link that says tutor.com from Canvas, yeah. Mm-hmm.